on the citation matrices and counts the lifetime contributions made by scientists from 1960 to 2019 and their single-year contribution based on 2019 Scopus data, Elsevier Research Intelligence, and SciTech strategies. Professor C.K. Jayashankar's name has been figured both in Indian scientists of all time, 64th rank out of 79, as well as in 2019, 49th rank out of 155 under applied physics. Also, scientometric analysis of rare earths research in India, published in Current Science, lists Professor Jayasankar as one of the most prolific Indian authors, fourth rank out of 20 in the field of rare earths research in the order of Z index. He is also elected as Fellow of National Academy of Sciences, Allahabad, India. The research activities of Professor Jaishankar are of both fundamental as well as applied in nature. These research activities have been supported by a wide variety of government and industrial organizations, both from India and abroad: Germany, UK, Italy, Spain, Mexico, Thailand, Portugal, Indonesia, New Zealand, and Australia. He visited USA, Europe, Mexico, Canada, and Asia under various capacities and assignments. He has published 307 papers in peer-reviewed international journals with citations as per Scopus, citations 8,332 and H-index 52, and as per Google Scholar, citations 9,757, H-index 55, and I-10 index 203. He guided 28 PhD and 10 MPhil students. His systematic and uniform studies on rare earth against radiation advanced the state of knowledge in the rare earth spectroscopy substantially and strengthened for the better understanding and design of optical devices based on rare earths. Now I invite Dr. C.K. Jaishankar to deliver the invited talk.
Okay, thank you very much for, and I thank the St. Joseph College for Women and all the conveners, administrators, and the members of the conference who are very kind enough and giving me a chance to share my knowledge on recent trends of rare earth doped nanoglass ceramics for photonic applications under the umbrella of nanotechnology and material science. And for the past 3 to 4 decades, I am working in the field of rare earth doped glasses, glass ceramics, and nano glasses. The previous speaker already mentioned a number of times the importance of rare earth magnets, ceramics, and so on. So, in this direction, we are able to work on rare earth doped glasses, glass ceramics. And in this talk, I am going to share how far we are able to get benefit from the rare earth based glasses, which are having potential applications in every field, either today or tomorrow or earlier. You can see, without seeing glass, without touching glass, without using the glass, it is impossible to complete our life. Day in and day out, we are able to use the glasses. That glass may be a drinking water glass, or your watch, or your laptop screen, or your TV screen, or window glass, whatnot. So everywhere there is a glass, and those glasses are having not only just decorative, but also in science and technology, particularly glasses of nanotype, are having potential applications, which I am going to share. And therefore, I am really highly thankful to the organizers giving a chance to have my knowledge, and so that you people get benefited and you can plan for future research in this field of in this potential field. Education is not the learning fact, but the training, inspiring of the minds to think. So, just you see, whatever you listen, not you are going to be just stop after listening, after completing the seminar. What all you gained from these lectures, from these conferences, and from these talks, you should think of how best you can contribute for future endeavors, and whether our talk or topic or the conference is having any value of inspiration, creativity. So this we have to think, not simply listening the conferences, but you have to make use of the talks and the subject. And now you have to inspire yourself, and creativity is very very important. That's what quoted by the great genius scientist Albert Einstein long long ago. And now you see, today we are able to conduct the e-conference. This was the e-conference was forced to conduct only because of pandemic environment, because people cannot gather together. I mean, social interaction is used to be totally forbidden because of COVID-19. And my dear friends, and the other way or indirectly, it is also very very helpful for people who are really want to do active research, or they want to sharpen their minds. For example, isolation is the best way to think, to concentrate, to do something. For example, if at all you are able to see old Mahabharata, Puranas, or whatever it may be, Rishi will go to forest where he will do tapassu, because where there is a loneliness and calmness will be there, so that his mind will be concentrated, and definitely he will achieve whatever he want. And it's the same thing what happened is, Sir Isaac Newton was forced to in quarantine during plague epidemic, and now he was sitting in the garden and is able to see how and why and what is happening when apple is going down towards the earth, not going up. And now he's seriously thinking, inspired, and he has created, and now he has put forward the gravitational force for any object. So because of gravity, the apple is attracted by the moon, by the earth, and now isolation is really helped him a lot. Similarly, we people have to make use of this pandemic environment, what best we can do, so that we can do something in future. And I mean, we have to face any challenges in these circumstances. So creative ideas can be obtained, can be created only when you are isolated. So make use of this, stay home, stay safe by using e-conference or WhatsApp messages and so on. And now you see, your title of the topic is conference is nanotechnology and material science. And my dear friends, and the same title, what I can say this: electromagnetic waves, advances in material science, and computational capabilities. These are the three fundamental components that makes our science and technology growing day by day and meeting our requirements as best as they can. For example, you see, electromagnetic waves are nothing but the light coming from the sun, artificial light. Of course, with your science and technology, you can naturally produce the sunlight. And now advances in material science, and now without material nothing. This is a material world. Material science is where you need materials for everything. For example, to sit on the chair, or to wear the dress, or to take something, a material is needed, and those materials are developed day by day, having multiple applications and durability and so on. And the computational capabilities, previously people are used to do multiplication by hand or some calculator or whatever it may be, 1 into 2 or 3 into 2. And today the computation capabilities are so rich, you can do in any calculations with no time, just one stroke. For example, today people are able to get the COVID say, take us or injections or whatever it may be. As on today, how many are deceased worldwide, or even within India, or within Andhra Pradesh, or within Kerala, and how many injections are given today and tomorrow what, and so on. Everything can be obtained with no time. That is the computational capabilities. And now these are the three stepping stones in science and technology. For example, electromagnetic waves I told, and understanding the electromagnetic waves and its properties, how it can be generated, and then how we can manipulate the generation of light, then you are able to get the lasers. Laser is nothing but the light emitted by a source due to stimulated emission All other sources, including sun or street light, whatever it may be, all are based on spontaneous emission. And now, if at all you are able to produce light with stimulated emission that is having extraordinary properties like directionality, intensity, monochromicity, and coherence, these extraordinary properties makes every applications. You tell me whatever work application you need, lasers are going to be directly or indirectly play a significant role. And similar advances in material science, for example, if at all you want to generate heat, the old people are able to burn the woods or coal. And today we are able to produce the energy not by burning the wood where the pollution, and similarly coal is also polluted, polluting the environment. And today you can produce the heat to electricity. Even then, if at all you are using electricity, it takes some time to get high different temperatures at different times. But with the induction method, you are able to get whatever temperature you want within no time. I mean, within a second, I can get the electricity heat by with electricity to a technique called induction. So these are all mainly because of advances in material science, and as usual, the computational capabilities. These are the three key factors or pillars today's science and technology, in which nanotechnology and material science is really playing a significant role. The college has chosen a best topic so that you can understand what is going on, what are still required, and when can we make those things still possible for our future endeavors. That the main of the conference, and the people who are listening this talk, I am quite sure this will be a stepping stone to strengthen their knowledge, either electromagnetic waves or material science or computational techniques. And definitely either of them or all of them are going to be rich in our research field. That's what I am expecting in this conference. And my dear friends, as I told you, electromagnetic waves is the best one. For example, if at all you are able to prepare any material, material characterization is very, very important. Either nanomaterial or bulk material, or Professor Beckman already told many times, analytical techniques like X-ray diffraction, FTR, this and that, where electromagnetic waves have been used as a tool to characterize the material. So without electromagnetics, there is no advances in material science. Without electromagnetic waves, there is no computational capabilities. For all those things, electromagnetic waves are very, very important. Knowing the importance of the electromagnetic waves, there are some credentials for the growth of electromagnetic waves. For example, you might heard Children's Day, Science Day, Teachers Day, Valentine Day, all those things. Each day is having so own importance. For example, Children's Day is meant for Dr. Sarvepalli Radhakrishna, and Children's Day is meant for Jawaharlal Nehru. And similarly, Teachers Day is meant for Dr. Sarvepalli Radhakrishna. Similarly, Science Day is meant for in memory of Sir C.V. Raman, because that is the day where the science was born. And similarly, this is within India. But you see, today, the entire world is controlled or monitored or evaluated or helping under the umbrella of United Nations Organization in order to encourage science and technology, as well as in order to salute the earlier people who have contributed their life towards science and technology. The United Nations Organization has named 2005 as International Year of Physics, because there is significance of International Year of Physics, because exactly in 1905, I mean 100 years back, Einstein wrote three famous research papers. One is photoelectric effect, theory of relativity, and Brownian motion. Of course, there is stimulated emission also there. All these things have been changed rapidly, science and technology. Without those fundamentals, without those breakthrough inventions, it is impossible to see the science and technology today. And that is why 2005 has been named as International Year of Physics, because physics is the key point for all sub branches of science and technology. And similarly, my dear friends, 2015 has been named as International Year of Light. You see, 2005 is International Year of Physics. 2015 is International Year of Light, because exactly the 1015 there is a first book on optics, because optics is the only tool, as I told you, to understand the universe, or to characterize the materials, or to measure whatever it may be. So in 1015 there is a famous book on optics written by Al Jahan, who has written the fundamentals of optics. So, in order to celebrate the contribution of Al Hazan and the famous book on optics, 2015 has been called International Year of Light. And my dear friend, similarly, 16th May is going to be celebrated International Day of Light, like Science Day. We are celebrating 28th February as Science Day, because on that day, Raman has invented very important physical tool to analyze the material through vibrational frequencies. And similarly, 16th May is the day where the laser was born. So wherever there is analytical technique, wherever you are able to see an application or characterization of the materials, either nano or bulk materials, lasers are being used widely as both science and technology, medicine, communication, even decoration or entertainment, whatever it may be. So by knowing the importance of the lasers, which was born on 16th May 1960, and therefore 16th May has been celebrated as International Day of Light. So you can see what I have given some examples that clearly indicates the importance of electromagnetic waves. And now, without light, there is no life. Life is light, light is life, and enjoy life with light. So life is going to be challenging with the only the help of light, by seeing, by making use of it, or enjoying with it. And now just to see, when you are talking about nanomaterials or material science or bulk materials, whatever it may be, each material is made of molecules. Again, molecule in turn is made of atoms. You see, in periodic table, there are more than 100 elements. Combining these, understanding these elements individually, as well as by combining these two materials, one can prepare variety of material, infinite materials. No doubt, in nature, all these materials are available, but you can artificially synthesize in such a way, you can make different molecules, different complex, so that you can get a specific applications, whether it may be useful for battery or satellite, or battery, satellite, or energy saving, or nanomaterial, whatever it may be. Everywhere there is an atom. So understanding an atom is the first step, and then a molecule, then a complex, then its application. So whether nanoscience or nanotechnology or bulk materials, or tomorrow you may get another field of material science, everywhere, without atom, without understanding atom, it may not be that much of easy to understand the entire world of materials, in particular nanotechnology also. And now, just to see, that's only an individual atom. When two atoms are combined together, it will be molecule. Once a molecule is formed, there are so many atoms might have combined. For example, if you take two atoms of a molecule like O2, N2, CO, or NO, these are all diatomic molecules. And there it may be a homo or heteronuclear molecules. Homo means O2 is a homo. Hetero means CO is a heteromolecule. So when two atoms are combined, when it formed a molecule, for example, oxygen and carbon, and oxygen carbon, once these atoms are coming together and made a molecule, there might be a vibrational energy of those molecules, and depending upon the molecular atomic size and atomic radius and its charge radius and the valence state, these molecules produces some vibrations. Those vibrational motions are very, very important. In solid state physics, they call it as a phonon. So an atom becomes a molecule. Once a molecule is happening, and now what are its vibrational rotational energies? Most of the material properties, either physical or chemical properties, will depend upon these vibrational energies. These vibrational energies are very, very important. And my dear friend, these vibrational energies can be studied through infrared spectroscopy, Fourier transform spectroscopy, or through a Raman spectroscopy. But out of these three, Raman spectroscopy is very, very useful, very, very precise information, and you will get with no time. And that is why Raman effect is famous. to understand the vibrational and rotational energies of the molecule. Without evaluating the vibrational rotational energy of any molecule synthesized or artificial available molecule, you may not have any practical application. So you take any nanomaterials or material science, there is a topic. The topic has been used to understand those materials, in particular vibrational rotational energy. So the Raman effect or FTR spectroscopy or infrared spectroscopy will tell you what are the vibrational energies, whether it is a faster vibration or lower vibration, what is ionic bonding, what is covalent bonding, and also whether the molecule is linear or non-linear. Once it is linear or non-linear, then antisymmetric, asymmetric, anti-bonding, all those things are very, very precise and characteristic bonds for any molecule. Each molecule is having its own vibrational motions, rotational motions, and those are fingerprint for that particular molecule. Why you are calling fingerprint means every human being is having his own fingerprint that will be never before and never after. But we even within the family, even in the own family, the fingerprints are going to be different. So each man is having his own fingerprint, and that's why we are going to call this as fingerprint analysis can be obtained with Raman spectroscopy. And my dear friends, where if at all you are preparing a material, and in order to understand the vibrational, rotational, or electronic, whatever it may be, you are going to allow electromagnetic waves to a material, and the material interacts with electromagnetic waves. The interaction may lead absorption, scattering, reflection, refraction, that I will tell you later on. Everyone knows that there is an absorption. So material, any material is having its characteristic energy levels, E1 and E2 and so on. The energy may be absorbed. Once the energy is absorbed, and now the atom or electron goes to upper state after taking energy from the outside, the energy, incident energy. And now, once the atom gets excited, and this has to release its excess energy, which we call emission, because the excited atom is more unstable, and when the electron is in the ground state, is stable. So the atom requires its stable state. That is why spontaneously it will release its excess energy, and the atom comes to the ground state. So this is called spontaneous emission. And now the absorption and emission depends upon the molecule or atom or ion, and each one is having its own characteristic frequencies. This is what we are going to evaluate. For example, there is an atomic system. When there is a molecule, in the molecule there is no way of having only electronic levels, because electron may jump one orbit to orbit, other orbit. A photon is allowed to interact with a matter, and now once after interaction, the various phenomena will take place that include transmission, absorption, scattering, and emission, diffraction, etc. And your analytical tool will allow you to measure either absorption or scattering or emission and diffraction. And this interaction may be modulate energy of the incident photon, or intensity, or polarization, coherence, or phase. Any of these properties, or partially, or all the properties get modulated. That depends upon the material. So by measuring the diffraction or emission or scattering or absorption or transmission, one can precisely evaluate the matter. That matter may be a nanomaterial, or you have synthesized the material in laboratory, or a material naturally available. So by using any of these techniques, one can precisely understand the material properties. What is the material, what type of material was made, what are the atoms or molecules, what is the bonding, and what is the ionic bonding or covalent bonding. Everything can be obtained by using the analytical technique, only just by interacting a photon with a matter. This photon may be an X-ray region, or maybe visible region, or radio frequency, or whatever it may be, and any of the properties, or partially or all, maybe get modulated. That modulation will reflect the matter, and that's what we are using. And now we are concentrating on the glassy materials instead of other materials that may be material important for electric material or magnetic material or battery or whatever it may be. Our entire research is going to be used all these techniques to characterize the glasses, glass ceramics and nanoglass and phosphorus materials and so on. And now, look, see, once a scattering will take place, I mean, it may be due to absorption or emission or transmission or refraction or reflection, diffraction or luminescence. And now, for example, if at all the material gets absorbed or emitted, I can extract the energy levels, then I can modulate for getting the stimulated emission so that I can get laser. And because of transmission properties, it can be used for communication. Similarly, because of refraction, I may see whether the crystal or a material is made of uniaxial or biaxial. And because of reflection and transmission, that will allow you to evaluate luminescence for any human beings, whether you want to lead your life. There are two things are very, very important: vision, audio and video. Both audio and video is possible only if at all material emits some light. Light may be a colored light or whatever it may be, a luminescence phenomenon is present because of a material is having and improved its functions by using the luminescence technique. And now, just you see, you take any conference, there are so many subtopics. For example, even your international conference, you have mentioned so many topics, and all topics with just mainly because of material science. I mean, physics and chemistry of materials, and then that material may be made of bulk material or micro material or a nano material. And there are so many applications everywhere. There is a glass material, and those glass materials can be understood, characterized, and then fabricated and developed for specific applications by a technique called spectroscopic technique or analytical techniques. And now, you see, spectra is nothing but ordered arrangement of release or absorbed energy of an atom or molecule or ion. So when you photon interacts with the matter, that then matter releases and you are able to arrange the energy orderly. And now, depending upon the position of the energy levels, I am able to qualify qualitatively and quantitatively. I can measure the material. For example, some materials may not emit or some may not absorb. And now, in those materials, I can, you see, sense to you see, can absorb or emit. If not, maybe induced. I mean, I can add a material which you can emit or absorb, and that emission and absorption depends upon the environment, because a material is spectroscopically not at all active. Now, I will put one active material in that material. This active material is surrounded by a material which is spectroscopically inactive, and now this active material property will change depending upon the environment. Previously, environment is inactive, spectroscopic inactive. By putting an active material, and now I can see what is the surrounding. For example, you know, ruby laser, Al2O3 is an inorganic, inactive spectroscopic material. If I dope chromium 3 plus, chromium 3 plus properties will be modulated in such a way you will get stimulated emission. So, as independently Al2O3 and chromium 3 plus is no more useful. But you combine these two things, you will get stimulated emission. Same chromium 3 plus, if at all it was surrounded by another environment, you may not get the stimulated emission. Similarly, instead of Al2O3, if you chromium 3 plus, if you put another nickel or cobalt or whatever it may be, you may not get the emission properties due to stimulated emission. So all depends upon the active ion and its surrounding ion. If the surrounding ion is spectroscopically inactive, you can induce those materials by using an active ion, so that you are able to evaluate the inactive materials also by doping an active material. That is spectroscopic technique. Sensitive to environment and structural composition. So if at all a spectroscopically active atom is embedded in a spectroscopically inactive material, and now spectroscopic properties will change the active material, and that will allow you to understand the environment, structural geometry, and so on. And now, look, see, there are so many materials, liquids, gas, and solid. There are so many materials. Out of many materials, crystal solids are crystals, glasses, powders, semiconductors, etc. And out of these materials, glass is the only material that can be fabricated from bulky to complex, miniature size to bulky to complex, miniature sizes. For example, you see, glass is the only metal, as I told you, complex miniature size, nothing but fiber optics. You see, fibers are made of clad and core. Core is surrounded by clad. Altogether, core and clad is diameter is not more than even 100 micrometers, or even sometimes even 50 micrometers. It is just comparable for human hair. And now you can draw this one even kilometers together. No other solid material can be made of fiber of compared to the fibers made of a glass. And at the same time, glass is the only material can be used, can be fabricated window glass, so bulky sizes. And my dear friends, whether you remember me or not, today we are having a cell phone. That cell phone has been replaced by watch, so there is no need to have a separate watch. Your cell phone is having a watch. Similarly, your cell phone contains a camera, so you don't want to buy a camera. And similarly, your cell phone is having a memory device, calculator, and everything. So all these components have been put together and made your mobile phone. And similarly, today there are buildings constructed by a glassy material. There is no steel, there is no wood, there is no cement, nothing. Everything is made of a glass only. So glass is such a peculiar material that replaces everything, including science and technology, or monuments, or buildings, or whatnot. You can say like that. And now, just to see, once upon a time, glass is only a decorative, but now it is a very special and technologically very important material. Similarly, once we named rare as maybe rarely available, but now it is used everywhere, everyone, anytime in our day, in and out, in all our walks of life, in all science and engineering, medicine and technology. For example, you see, glass, once upon a time, if we go to temples and monuments of port, you can see a glass instead of a steel. So glass is such a old material. Those have been used only a decorative purpose. Today, your laser gain media, your display devices, your fiber optics are made of glasses only. Similarly, Professor Beckman already told in Kerala there is a rare earth industry, but I know that one. In Cochin there is always where there is a rare earth industry, and there are so many raw materials are available, and they are able to extract rare earth materials in those raw materials. Once upon a time, those materials have been called as very, very rare, because you will get only micrograms after cleaning, extracting tons of the raw materials. And that's why it is called rare. And now, my dear friend, everywhere there is a rare earth. For example, your display devices like your telephone, your television, your laptop, and your mobile phone, all those screens are made of with rare earth elements only, that I am going to discuss later on. And those different rare earth elements are able to give different colors, which is far better than transition elements. No doubt, the transition elements like copper, nickel, cobalt, vanadium is having colors, but those colors cannot be modified, modulated. Durability and fabrication is very, very difficult. It will disintegrate and degrade with no time. Whereas any material made of rare earths, the colors are very, very sharp, and in a long run, it is really going to be very, very good and look like a very new material, because degradation losses are very, very less. And that is why everywhere rare earth elements are playing a significant role. So rare earths are no more rare. It is common everywhere, particularly in science and technology. And now, for example, I am showing you. You see, this is the port. You can see in windows is decorated by glass. Your chemistry lab, you can see all these things. And now the jar, and even the beverages, and your cooling glass, or goggles, and your lens, and your mobile phone screens, and just to see watches, helmets. Everywhere there is a glass. So Glass is such a beautiful and useful material everyday life. And now, if at all you see, if at all you want to, you see when you are in a presentation, you are using a semiconductor laser as a pointer where the power is very, very less. If at all you want to get high power and high energy, the laser gain media should be only in a glass, because the energy gain will be amplified, enhanced if the gain media is little bit longer. So it depends upon the dimension. So only a glass media will be a gain media to get high energy and high power. So that is the useful of the gain active media in lasers. And similarly, as I told in fibers also, glass is the only material in which you can transmit optical signals. This optical signals will have interface whatever information you need, audio or video or text material, whatnot. If it is digitized, those digital data can be optically synchronized. So optical data will carry forward, will be taken care by an optical fiber, so that you can communicate your communication from one end to other end. Those ends may be within the city, or from city to city, or within the continent, or one continent to other continent, or even from earth to satellite. So everywhere there is a fibers that takes the information from one end to other end. That is the beauty of the glass. And now once you come to a glass, there are different types of glasses. The glasses are made of phosphate glasses, or silicate glasses, or telluride glasses, or germanate glass. There are so many different glasses are available. And now, once there is a phosphate glass, you can add some modifier so that you can change its properties. As it is phosphate glass or silicate glass, its properties are restricted. If you change a modifier like alkali, alkaline earth, or heavy metal oxides, and now a property can be modulated. And similarly, the dopants, you can dope D block elements or rare earth elements or any elements as you like, depending upon that material fabrication is useful for mechanical properties, optical properties, thermal properties, magnetic. Depending upon the property you want, you can you dope those materials so that you can prepare a material. Now, once there is a glass former and glass modifier and dopant, you can choose as many glasses. There is no death for preparing new classes in your in future, throughout your career. Forever you can prepare new glasses and new properties, so that those properties may be enhanced one, or preparation technique may be easy, or is cost effective. Everything you can keep on doing. For example, if you go back 50 years back, in the market you can see only Lifebuoy soap and surf powder. Today if you go to market, there are so many different types of soaps, and there are so many different types of detergents. Do you think that is an end? No. Tomorrow you may get new soap, new detergent powder. Similarly, today there are some glasses, and tomorrow you are going to see many more glasses. So there is no death for research in materials based on glasses, and every day you can produce one new glass. Like polymers in organic chemistry, there is a polymer. Every day they take one carbon out, they can put one of the another molecule. So you keep on breaking the carbon and adding one more molecule, the poly cycle will continue. Similarly in glass also, you can prepare as many glasses as you want. If at all you are lucky enough, you may get a good glass which is replacing the existing one, or some way it may be useful. Some way, for example, velocity of light can be measured so many techniques, but there are some techniques. There is one technique. It may be easy to measure. It may be more accurate. So there are so many methods, but there is a method. It will be easy to measure the velocity of light, and it is more accurate. Same thing here also. You can prepare a glass. The glass may be prepared easily, but it will be very useful. Like that, the research continues. That's what people have to do, the creativity and inspiration. What are the classes, existing classes, and what are the physical, mechanical, thermal, optical, and magnetic properties, and how these properties are varying from one glass media to other media. So you analyze the materials, and now where you can improve is very, very important. I mean, if you take alkali, alkaline earth, and heavy metal oxide, for example, lithium, sodium, potassium, alkaline earth, barium, calcium, strontium, heavy metal oxide, niobium oxide, tungsten, indium oxide, like that. These are heavy metal oxide. So keep on changing these materials. you can improve the properties, physical and chemical properties of glasses, so that it may have some practical and improved, enhanced applications. That's what I'm telling. Just to see, what I'm telling is glass former, modifier, and activant. All together, it will be 100%. So you see, 50, 49, and 1 is 100, and 60, 39, 1, 70, 29, 1. So you keep on changing the composition, you keep on preparing the glasses. And my dear friends, if you know the core and clad, the refractive index of core and clad will change only 0.1%. So for 0.1%, there is no need to change 39, 49. You can use 60.5 and 38.5. So even zero point 0.5 molecular weight or percentage, mole percent, will change its optical property. For example, to get total internal effect, reflection in fiber optics, you are going to change only 1% of refractive index. So 1% of refract can be easily changed, not by changing 1 gram. I can change 0.5 gram, or I can change 0.5 milligram. So you have the technology, you have a machine in such a way, you can measure the materials milligrams or nanograms. So keep on changing the molecular composition, stoichiometric ratio. You can prepare infinite number of glasses only by changing the former, modifier, and activant. And now, my dear friends, the former and modifier, in some modifier, you are telling that alkali elements. I can use alkali and alkaline earth. Not only alkali, but also I can use high metal oxide, high atomic number. So keep on changing the materials. I can prepare variety of glasses, and I can modify the properties so that I can use for practical application. Similarly, how a glass can be prepared, very very easy technique. Nanomaterials preparation and characterization is very very expensive, whereas the preparation of the nano glasses are very very easy, and you can do research in nano glasses and glass ceramics better than nano materials, because the preparation of nano materials characterization is very very difficult. It requires lot of engineering, whereas preparing a glass is very very easy. You just take the raw material, weigh them and grind them, and you melt them through a platinum crucible, depending upon the how impurity you are going to minimize. Whether it depends upon the glass material, and in order to minimize the impurities while melting, you can use platinum crucible, or silica crucible, or aluminum crucible. Even sometimes they use a porcelain crucible. They melt it and they pour it and again anneal it, and this is the glass what you are getting. And now, as I told you, there are so many glasses, and there are analytical technique to characterize them. And now, just to see, suppose let us say phosphate glasses surrounded by ligand, and this another type of ligand, this another type of ligand, and the bond angle, bond length may be different, and depending upon the ligands and the surrounding atoms and the central metal ion, you see band position, as I told you, the wavelength, and now off width of the peak, I mean the off width, and area under the curve, and any of these properties may change depending upon the ligand environment. So if at all you want to use this material for an optical devices, for display devices, I can tune its emission position or absorption position, I can tune its off width, and I can choose the area under the curve. So these are all the factors I am able to measure, and I am going to call it as stimulated emission cross section, or absorption cross section, or off width, and area under the curve is called as a branching ratio. So just by changing the environment, by changing the active ion, and by changing the modifier and the activator, I'm able to prepare a variety of glasses. I simply measure these characteristic values, and finally I will evaluate. So already there are some glasses, and I compare these values with the existing glasses, whether my properties are improved or not, and then I can tell whether it is having a practical applications or not. And now just to see, and once I prepare a glass, my first step is what is vibrational frequencies. As I told you, you can use infrared spectroscopy, or FTIR, or Raman spectroscopy. So these are all vibrational frequencies of a new material, and with this I am able to say whether the material is made of silica or phosphate or OH bonding, non-bonding oxygen, and so on. There are so many information I can evaluate by understanding, by measuring these the vibrational frequency of a new glass or any material. And now, just to see whether it's a phosphate glass, silica glass, or chloride glass, these are all the phonon energies, a vibration. We call it a phonon energy. The solid state people will call it the phonon energy, and optical and spectroscopy people will call vibration energy. And depending on the glass, the vibrational phonon energies evaluate. So you can see different glasses are having different vibrational frequencies. I mean, different phonon. This will help us whether those glasses are having practical applications, particularly whether these glasses are having any luminescence. I mean, colors. Luminescence means you can see a tube light or filament lamp or street light is having white different colors. Those are, it gives some light, and it may be a white light or a single color or multiple colors. So all those colors can be modulated by depending upon the phonon energy of the system. And now, just what you are telling is, just you see how actually the absorption and emission work is as follows. For example, when the photon is falling on a material which you are preparing a glassy material, when photon is allowed, the absorption will take place. And once absorption is taking place from ground state to excited state, and the excited state is more unstable and it relaxes towards the ground state, which we call it as emission. Here, one important point, whoever is doing research, whether physics, chemistry, or whatever it may be, they are missing the fundamentals. Please remember, the absorption is a single step, and once it goes to exit state, and now while coming back, it may not be a single step because there are so many other levels are there in between. So it may jump to this level, this level, this level, then finally to this, because here the excitation you are using the energy prescribed photon energy, so that if the energy level and the incident photon matches, then only absorption take place. Whereas here it has to come down. While coming down, it may not come directly to the ground state. Sometimes it will jump here, it will jump here, it will jump and it will jump here. But this is what I am showing. For example, one photon goes from ground state to excited state, and now it is coming, and then from here it jumps, because you see here I am showing the wavy line, here I am showing the solid line. And what is the difference between this is the excess energy is converted into the form of non-radiative, which I am showing wavy line. And now here solid, this is a radiative. So depending upon the phonon energy, that depends upon the environment, active ion. So depending upon the phonon energy of the material, sometimes non-radiative may be dominating, sometimes radiative may be dominating, or both are equally competitive. And now, depending upon the environment, non-radiative and radiative can be modulated and tuned for our purpose. For example, I want to get the emission, intense emission for this line, so that may be possible in some environment. Sometimes if I may get 579, and depending upon the environment, 579 may be better intensity. So when you do absorption and emission, radiative and non-radiative processes are very, very important. And now for display devices, non-radiative should be as minimum as possible, and radiative will be as much as you can. Then only the display devices will work perfectly and changes from one color to other color spontaneously, so that our human eyes may not distinguish the change, because you can see red, white, blue, or what different colors simultaneously with no way, so that you cannot recognize the change of the time. So that is very, very important. I mean, switching from one color to other color and recognize it by eye is so important. And now just to see, what I am telling is, I have prepared so many glasses. These are the, we can see I have kept in a graph sheet, and you can see 10 centimeters by 10 centimeters, 5 rods, slabs. These are all the glasses I prepared in my own lab and having some importance, and particularly these glasses are useful for laser development. And now you see, my topic is, as your information, you are stressing that nano glass, nano materials, nano technology. And now what I'm telling is, here you can see in this diagram, this is a transparent in some portion, in some point there is a dot. So a glass can be made into a glass ceramic. When you take the X-ray diffraction of a glass, you will get a peak without any sharp diffracting pattern. The glass can be converted into glass ceramics very easily, because once a glass is prepared, I can anneal, I mean, I can keep that glass in a particular temperature, particular duration, so that I can nucleate nano size crystallines inside a glass, so that a glass becomes nano glass, or I can call it ceramics. And now that once a glass becomes nano glass or glass ceramic, the first observation, the first restriction or first consent is the glass should be a transparent. You see, you keep on inducing the crystalline inside a glass, the glass transparent, the glass becomes opaque. So we have to play in such a way. You have to choose the temperature, you have to choose the duration. At particular temperature, at particular duration, the glass can be converted into a nano glass. So once there is a glass and nano glass, always there is an advantage. Whatever optical properties you are getting a glass, in the case of nano glass, you will get superior properties. That's what I am telling. So similarly, a glass can be converted into a glass ceramic or nano glass. Nano glass. I mean, inside a glass, I am able to nucleate crystallinity, and so that the optical properties will change. And now just you see, I'm just giving a decay curve is very, very, because you see luminescence materials means how fast the light emits and how fast it changes from one color to another color. All depends upon the decay. I mean, once the atom gets excited state, it will come back. While coming back, it is called a decay, deintegration. And now this decay time is very, very important for any display devices. For example, you can see a black line is a glass ceramic, and sorry, glass, and blue and red is a glass ceramic. And this decay is time is very, very less, whereas this decay time is very, very long. So in a glass ceramic, I am able to see the lifetime is longer, whereas the lifetime is shorter. So a glass becomes glass ceramic, and I had an advantage of lengthening its lifetime. So this is the way how optical properties, particular luminous properties, can be enhanced from glass to nano glass. This is what we are doing. And now just to see, is a normal glass where this is the active rare earth ions. And now the glass may become a glass ceramic. Just to see, this is the round bubbles are nothing but glass ceramics. And now you are doping the rare earth ion activator ions. So those activate nowadays, the activator ions are available in the nano size also. And now I can dope the nano lanthanide so that a glass becomes nano glass. So just to see, this is a normal glass, and this is the glass converted glass ceramic, and this is the glass where the nano crystals are doped. And now you can see the density of the lanthanides. The normal glass, the density is less. In glass ceramic, the density is little bit enhanced. Where in the case of nano crystals or nano glasses, the density has been enhanced very, very much. So automatically when the lanthanide density has been changed, improved or enhanced, automatically its luminescence properties are going to be enhanced. So in a nano glass ceramics, I am able to get enhanced or improved, increased luminescence properties. And now just to see what I am telling here, this is the glass composition. And now phosphate is the glass former. K2O, Al2O, BaO is nothing but modifiers. Nd2O is active ion. So K2O, Al2O, BaO I am adding such a way I may modify its physical properties such as density, mechanical properties, thermal properties, transparency. Of keeping all those minds, I am using different modifiers and I am changing the neodymium oxide. So depending upon the glass composition, non-radiative, radiative are going to be vary. So my intention is how best I can enhance the radiative properties, and by changing the composition, I can do the research in the glass and I can enhance the radiative properties. So I can measure the absorption spectra, I can measure the emission spectra, I can measure the decay curve, and I know what is the glass composition. So I can optimize the glass composition so that which glass composition is going to give better luminescence properties. With glass, nano glass is going to give better luminescence properties. All those things can be done. This is my research. Instead of neodymium, I can use the entire rare earth ions, not only neodymium. I can use erbium, I can use thulium, I can use dysbium. There are 14 elements. I can choose whatever element I want depending upon the purpose, and I can vary the composition. Simply I can measure the absorption spectra, emission spectra, and decay, and now I can evaluate whether these materials are having any practical applications or not. Even if there is no practical application, I can get science of the material. You see, before going to have practical applications, you know the science of the material, what is chemical properties, physical properties, and these properties are very, very important, so that whether we can improve or not. To in order to improve, what type of modifiers I can use, what type of active ions I have to use. So science of the materials comes first, then only you can look for a practical application. So a science of material is very, very important. So if you do this one, you will get science of the materials, and then next step is what about its application, practical applications. And now, see, my dear friends, now I am telling how the display devices will work. For example, the white color is nothing but combination of blue, green, and red. And one rare earth ion called cerium, the other one is terbium and europium. These are the three elements. One gives blue color, one gives green color, the other one gives red color. And now, if you combine these three elements properly in a proper composition, you will get a beautiful light. And similarly, if at all you are adding only cerium, you will change the blue color, light blue, thick blue, average blue, like that. So you can choose these ions, and you can choose an environment, so that I can optimize the glass composition, ionic rare earth ion concentration. I can get either white light, or I can get blue light, or green light, or red light. So what is the color density and so on, I can do all those things. For example, you just see, this is the way how a color glass or your display devices work. Blue, green, red is the perfect color. Main colors. I mean, when blue, green, and red are added together perfectly, you will get white. If only red and green are added, you will get yellow color. And blue and green are you will get cyan. And similarly, red and blue will get magenta. So by keep on changing these colors, you will get infinite colors. For example, if you go to class shop or if you go to paint shop, they will give infinite number of color of paints and a color of dresses. So how those things have been made just by changing these colors, and so that you can get what color you want. So once you change the color, our human vision is very, very important. You see, some people may prefer red color, some people may prefer blue color, some people may prefer green color. But if you take the statistics, you can say most of them are preferring white color. Just to see, most of them prefer white color or cement color or navy cream color, like that. So all depends upon our eyes attraction. So depending on our human eyes attraction, you can prepare the glassy material, and also by glass becomes glass. What all you make a nano glass, there is further improvement of the colors, so that our vision and attraction and our happiness will be enhanced day by day by using different glasses. And now, for example, you see, if there is a European red color, and if it is samarium, this is yellow color, and now thulium blue color, and dysprosium green color, cerium blue color, and terbium green color. So there are different rare earth ions having different colors. And now, if you go to next one, europium, terbium, and cerium, and this is the absorption or emission spectra, you can see not only europium is going to be red color, it also gives other colors. Out of other colors, red is dominating. Similarly, in the terbium, green is dominating. In the cerium, blue is dominating. And now, just you see, europium gives red color, terbium gives green color. And now, if I add together, and by changing the composition europium and terbium, I can tune from red to green or green to red. This is the way how research is going on. And depending upon the environment also, the colors are changing. So there is a research, plenty of research in glasses, and these glasses are going to be developed very easily even in degree colleges with minimum facility, where furnace is sufficient, the alumina crucible, silica crucible is sufficient, phosphates are cheap, silicates are cheap. Only expensive part is rare earth ions, but you need only 5 to 10 grams. So depending upon the rare earth ion concentration, combination, and host matrix, you can tune from red to green or in between. And similar, these are the emission spectra. And similarly, you see, europium is the red color, cerium is the blue color, and keep on adding these two atoms and changing their composition. I am able to tune red to blue or blue to red. And now this is the emission spectra. And now, my dear friends, look, there is a one nano phosphorus we have prepared yttrium, calcium, zincate, and there thulium, erbium, and yttrium. These three elements are giving three colors. And now, by changing, you see, I kept this yttrium, calcium, zincate constant, and I kept this thulium, erbium constant. Only I am changing the yttrium concentration. When I am changing the only yttrium concentration, I am able to tune from green to red. This is the research what we are doing. A non-phosphorus, how a color can be tuned from green to red. And now it is having a practical application. Similarly, the same things, this is called CA coordinate. The people who are working on phosphorus materials are rare doped colors. They know this is the green and this is the blue and this is the red. If these three are equally equal, then you will get a white color. This is bluish green, or this is greenish red, or whatever, it is yellow color. So green and red combined together, you will get yellow color. And now, how these materials are going to be not only just display devices, there are some sensors, optical sensors. See, sensors are really equally important field of research, and that you can do with rare earth doped glass also. For example, a rare active ion is doped in some matrix. In normal room temperature, this is the ground state, this is excited state, and this excited state are very close together. I mean, these two levels can be thermally populated. These two, E2 and E3, separation is so small, so that this can be thermally populated, and the relative population can be depends upon the temperature. At room temperature, this level is well densely populated, this level is upper level less populated. If we keep on increasing the temperature, this thermally populated level gets population, and now if we still increase the temperature, this level gets more populated. And for example, you see, at room temperature, this level is less intense and this level is relatively more intense. And now at average temperature, the both levels are equal temperature. When the temperature is more, the level which is low intensity at room temperature shoots up its intensity, this higher temperature. So this material can be used as a sensor to measure the temperature. Rare earth doped glasses or glass ceramics or nano glasses are going to be used in optical sensors also. Similarly, one more important part, for example, in solar cells, you see, in the case of solar cells, when the sunlight is coming on falls a solar photovoltaic cell, only 1130 nanometers are utilized, absorbed, and it converts to electricity. Remaining energy is unutilized. And now, if at all you are able to prepare a layer based on rare earth elements, I mean, those layers, what we will do is high energy will be converted to lower energy, and lower energy will be converted to high energy. I mean, up conversion and down conversion. And now this is the portion absorbed by the solar cell, and this is the high energy that cannot be absorbed by the solar cell, and this is low energy that cannot be absorbed by solar cell. And now there is a rare earth ion layer. What it will do is lower energy will be converted to higher energy, which is exactly equivalent to 1130 nanometers, to a process called up conversion. And similarly, this is the higher energy which can be converted into lower energy, which is called down conversion. So these are all rare earth based layers. Those layers will convert high energy to low energy to high energy. That exactly matches with the silicon solar cell. Previously, only this energy has been converted into electrical signal. Now you are able to convert even the low energy and high energy to a solar cell. So the rare earth based materials can also be used to enhance the solar energy. And similarly, just you see, previously, there is a battery word spoken by the Batman, and now there is an anode and cathode, and there is an electrolyte. These are the basic mechanism of a battery cell. And this electrolyte is amorphous material, and anode and cathode are made of crystalline materials. And now, what will happen is, when the charge carriers or electrons moving from one end to other end, previously there is a electrolyte made of amorphous, and this is a material made of a crystalline material. And now it has to move from amorphous to crystalline material, and again amorphous crystalline material to amorphous, because there is the interface problem. So in order to improve its efficiency, if at all all you are able to made a electrode or anode or cathode in a glassy material, one can enhance the battery performance. That's what people are working in the case of batteries. For example, you see a glass material, glass ceramic material, glass ceramic. A homogeneous network former for the electrolyte and electrode material would provide a continuity for the mobile ion surrounding during transfer from one electrode to the other, and would consequently reduce the interfacial polarization while transfer. So nowadays, most of the batteries and most of the people are working how to prepare a battery based on only amorphous material, because electrolyte is supposed to be amorphous material. It cannot be a crystalline material, whereas electrode and anode is a crystalline material. If at all you are able to make electrode and cathode amorphous material, definitely your battery performance can be improved. So glass, ceramics or nano glass are going to play key role for developing the batteries. And now there's another important point. We can call it the photonic chip. You see, integrated chips. Those are all made of electrical circuits components. And now you see, one fine day everything is going to work on only optical signal. Nowadays all your electronic circuits, whether in mobile phone or cell phone or in TV or laptop, there's a electronic circuit where the electrical signal has been converted into optical signal, again optical signal into converted electrical. So there is interface problem, optoelectronic electro-optic devices. And now if at all I am able to invent a device which will work only optical signal, and then there is no problem of interfacial problem. That's what people are expecting. And for example, this is a transparent glass material and this is a laser beam, and if the laser beam is allowed to fall and at focal point, and now this is a glass material, this is a transparent material, a laser beam is passing through a transparent glass material. At focal point laser intensity has been concentrated. The laser intensity is such a way, its optical properties, mechanical properties or thermal properties may change, because this material is irradiated with high energy laser beam. And now my intention is I have to enhance its refracting, because this material is having refractive index, and because of your laser pulse at focal point some modification will change, and my intention is I will change in such a way its refractive index will be enhanced, I mean increased. And now the original glass material is having one refractive index, and wherever the laser falls, that material refractive index is high, I mean. And now I can move with this glass slab or a laser beam so that I can draw a line. This line is having higher refractive index and the surrounding is having a lower refractive index. So a three-dimensional fiber has been embedded inside a glass piece. A fiber has been embedded inside a glass piece, and now erbium doped fiber amplifiers, Bragg grating. These are all nothing but optical signals may be amplified or reflected. I mean reflected means subtracted. So you can construct a grating of a fiber, you can construct a fiber of an amplifier, so that what the electronic chip will do, only electrical signals will be modulated by adding or subtracting or multiplication. So if at all you are able to embed a different types of fibers, I can manipulate the optical signals, amplification, subtraction, multiplication. So now this glass piece becomes a chip based on glassy material. So optical signal will do all manipulations what you do in electronic circuit. So a glass ceramic or a glass is going to be a photonic future. So we are lucky enough, we are able to prepare a glasses in collaboration with UK people. I have constructed a waveguide, that's what we call it, the waveguide, and those transmission properties are really comparable with the commercial fibers, and that is what we are working also. A glass may be future photonic chip. And now, you see, we are working on electromagnetic waves. Today, electromagnetic waves, particularly spectroscopic technique, are used not only to analyze the material, even in medical field, electromagnetic waves are very, very important. For example, I can collect salvia from a patient and then I can take the spectra. By seeing the spectra, I can say what type of salvia it is. Is it defective? It is normal. If it is a defective, due to what? At the same time, if it is defective, if it is due to corona, and now the peak positions intensity will change. So today there is a technique, and it is really in a progressive way by just taking the spectrum of salvia. I mean, what you are getting in your mouth, I can take the spectra and I can tell whether you are having not only corona, even all types of diseases can be evaluated, because depending upon the disease, in severity of the disease, the peak positions intensity are going to change. So this is spectroscopic technique, and this will be continued forever. And for example, this is temperature meter. By just seeing the infrared radiation coming from the patient, the temperature changes. So a thermometer can be constructed only with the infrared radiation. Similarly, your finger is kept inside the oximeter, and it will measure what is the oxygen ratio and what is the pulse rate. All are nothing but only spectral profile modulation. So spectroscopic technique, analytic technique is very, very important. That will be highly helpful to characterize the materials and to have any practical applications. That material may be a nano material or bulk material, and tomorrow there might be some other material. And similarly, that material may be naturally available or synthesized by you. And now you can differentiate synthesized materials, natural materials, and what is science of the materials. And spectroscopy technique is very, very important. Everyone should know from A to Z. And now we are lucky enough, we are doing research on glass materials, particularly nano glasses. We are getting an interesting results. And now, my dear friends, and our forefathers, our elders used to stay in attached houses. And today, the material science and engineering technology has been developed in such a way. Today, we are living in skyscrapers buildings. Similarly, previously we used to do mud vessels. Today, we are having a stainless steel, and it is a life warranty. Whereas this one is warranty as long as you carry carefully. And once you lose your time, concentration, and if you throw it, and it will make pieces. And now the materials have been evolved from thatched houses to the skyscrapers, and similarly like this. And same thing, as per Darwin, the human beings also developed from our forefathers monkeys. Today a stylish man. In this evolution, some people may become Einsteins or C.V. Raman, Bose, Abdul Kalam, and similarly Buddha or Krishna or Yesu or Allah. All depends upon you, how best you are able to use your brain with creativity. And inspiration is very, very important, and that is in our hand. A man may be born as a poor, but if at all you die a poor, you are the only responsible person. While at the birth you are not responsible, but at the time of death, if you die as a poor, you are responsible, because you have not made use of your genes properly, you are not practiced properly. That is in our hands. And now, see, take risk in our life. If you win, you can lead. If you lose, you can guide. This is what Swami Vivekananda. Similarly, a researcher in any profession, you may lose or win, and now you may guide or you may lead. So don't get disappointment, don't get excitement. Whatever you do, try to adjust the philosophy. This is very, very important. Whoever may be a researcher or scientist or a politician or a cricket player or whatever it may be, either you may lead or you may guide. Don't get disappointment, and all depends upon how you are able to develop your creativity, inspiration, either research or whatever profession you feel. And now, just to see, a poet was once asked, how do you remain cool in every situation? The poet answered, I just remind myself that I am made of mud and will return back to mud. Then why have pride and anger? This is what the philosophical statement. And finally, I thank, because training by my parents, teaching and guiding by teachers, blessings by relatives, friends and colleagues, and support from classmates and students, and finally cooperation from family members, from whom I thank, and the credit goes to all of them as mentioned above. Also, thanks for patiently listening the present talk, and looking for your comments to improve my future talks and to be active. My, if anybody is interested to got clarification, even not only now, they can contact me by email address, or they can contact me my mobile number. The organizers are ready to give you. And now with this, I thank you very much. I'm sorry for technical problems, and this is what best I can do. And that credit goes to you, and the credit goes to St. Joseph College for Women for allowing me to spend my valuable time for you. Thank you very much. The mic is over to organizers now.
Yeah. Thank you, sir, for your wonderful and highly informative session. Now I invite Dr. Julian Joseph to present the vote of thanks to Sir Jayasankar.
Good evening to everyone. On behalf of St. Joseph College for Women and PG Department of Physics, I thank Dr. C.J. Jayasankar for today's lecture on recent trends of rare earth nanoglass ceramics for photonic application. Through his lecture, we could understand the basics of research related to glasses. He explained different types of glasses and how to prepare glasses and also about characterization techniques. He also explained about rare earth glasses and application of glasses. So today's lecture was full of knowledge and it give deep insights into the topic. So once again, I would like to thank Dr. C.J. Jayasankar for taking out time from his busy schedule and enlightening us with his knowledge. I would also like to extend my sincere thanks to all participants for their cooperation and support. Thank you.